Greetings, Earthlings. This is your glorious professor uh, bringing you a special online version of ME 273, and the topic for this evening is numerical integration. So, we're going to be going through the numerical integration section of the slides for a course that I already have posted on the resources tab and our Saki course site. You know what I mean, right? So let's get right into it. This is going to be important for you to pay attention here um, in order to perform well on the next guided activity, right? So if you're not sure about something, I'm going to kind of go through this quickly. If you're not sure about something, you can always stop this and rewind and watch it again and think about it. By the way, there is a good chapter in the numerical methods textbook on numerical integration, and in particular the algorithms that I'm going to generate and show you in the slides here. You can also read about and get a little bit different description in the textbook. All right, so what are we looking at here? This blue curve is some generic function. Right? We've got the function plotted as a function of x, and I've got 2 points a and b indicated here. Our goal is to come up with a way to estimate the integral of this function between the limits a and b, and to do it numerically. Now, by definition, that's what this red coloring represents the area under the curve. By definition, the integral of f of x dx between the limits a and b is just equal to the area under the curve. You learned that in calculus. Right, so just to generate the importance of being able to integrate something numerically, what if we don't know a particular function? So for instance, let's say we've done an experiment where you've taken some data and you've generated data points, and you don't know what the function is, but you have to, with this data, analyze it in such a way that it's necessary for you to get the integral under the data points between some limits. Or another possibility is that you have some function, but this integral, the integral of f of x dx from limits a to b, does not exist. In other words, there's no closed form solution. In that case, there's no choice but to approximate it. And so the question is, how do we approximate the integral, whether we don't know the function itself or the integral doesn't exist? So one possibility, as you can see written down here, is to use rectangles. Right? So what I mean by that graphically is on the next slide here, and you can see what I've got. See these yellow things? These are rectangles. You all know what a rectangle is. And I've produced a number, let's see, 1, 2, 3, 4, 5, 6, 7. In this case, 7 yellow rectangles. They all have the same width, you'll notice, and I've constructed them with the same width such that all 7 fit perfectly between the limits of a and the limits of b over here. This blue line is that same function we had. And so you can see that it's perhaps not a very good representation of the area under the curve, but it's not too bad either. We can increase or do a little better if we use more rectangles, and of course if we're going to use more rectangles and make them fit between the limits of a and b, we'll need a lot more, as you can see in this slide, where you can count these and see how many I have. I've made the width of each one still equal, but certainly smaller than the previous slide. And you can see by making them thinner and including more of them, it fits the curve a little better, although maybe not perfectly. Right? So if you have a look, each one of these, by the way, if you look closely, the upper left corner of each rectangle is touching that function. It's touching the curve. See that? All right, and I constructed it this way on purpose. And so based on this picture, let's build an algorithm. All right? So if we're going to build an algorithm and we're going to use a computer to do the calculating for us, it's going to be beneficial to index positions in such a way that it makes it easy to program. So I'm going to just show you how we're going to index things, index specific positions, and then it'll make sense a little bit later. All right. So first of all, I'm going to let position A, that's the lower limit of integration, I'm going to let that be the same as position x with subscript 0. Right? You'll notice that that also coincides with the left-hand side, this is important, the left-hand edge of the first rectangle here. Right? Now, the height of that first rectangle is simply the function evaluated at that position x0 or a. Right? So that's what this represents, the height of that first rectangle. Right? So that is position x0, the function of x0, function evaluated at x0 is the left-hand edge. Let's look at the second rectangle, which is this one here. The left-hand edge I'm going to index or call position x1, one subscript. The height of the second rectangle is just the function evaluated at x1, or that. Right? That's the height relative to the x-axis here. Look at rectangle 3. The left-hand edge of rectangle 3 is x2. You can see how we're numbering things now. The height of the third rectangle is the function evaluated at x2. And you keep going this way with this labeling scheme until you get out here to the very last rectangle, which will assume there's capital N of these rectangles. And if there's capital N, the left-hand edge of the nth rectangle is x with subscript n minus 1. And of course the height of that nth rectangle is the function evaluated at that position. Right? Now, keep in mind that all the rectangles have the same width. That's what this delta x is right here. And that delta x can be very easily calculated by subtracting the limits b minus a. Remember, I've chosen a width such that all of these rectangles of the same width fit perfectly between a and b. If you take b minus a, divide by the total number of rectangles, that gives you the width of each one. All right? And so the way we are approximating the area under this curve is to simply add up the area of each of these rectangles. I think you can see, hopefully, we are underestimating on this side. See, there's gaps here. Over here, the rectangles are sticking above. Right? So it's not a very good approximation, but I think you can see that if I were to shrink these down even smaller, in other words, make the width of the rectangle smaller and use more of them, that we would get a better, even yet a better approximation. Of course, by definition, if we shrunk the width of the rectangles down to 0, then we're back to integral calculus. But remember, we either don't know the function or the integral doesn't exist, so we're going to stop before we get down to delta x equals 0. All right, so how do we build the approximation? Like I said, you simply add up the area of all the rectangles, and that's what this expression shows. Right? So here on the left-hand side is the integral of f of x dx, whatever that function is, from a to b. It is approximately equal. Now, each of these terms on the right-hand side is the area of the rectangle starting at number 1. So this f of x0 times delta x, this is the height, and delta x the width of rectangle number 1 down here. The second term right here, as you can see, f of x1 is the height of rectangle number 2, delta x is the width. Right? F of x2 is the height of rectangle 3 times its width, that's the area of the third rectangle. And you keep adding these up until you get to the very last rectangle, the nth rectangle, the height times its width. Now this can be expressed a little more economically by simply using a summation sign and factoring out the constant delta x term here. Right? And so you can see, hopefully, that the indexing is correct. If I add up all these terms from I equals 0 to n minus 1, I get the exact expression that I had written out above. Right? This also, hopefully, is familiar. This is a Riemann sum. Right? It would be an exact equation if we were to shrink delta x down to 0, which of course would mean we would then go to an infinite number of these rectangles. So remember, an integral is just a sum. An integral is just a sum that adds an infinite number of infinitesimally narrow things. Right? Well, we're stopping before we get to the continuum limit, and we're going to keep these rectangles finite here. Right? So this is called a Riemann sum. This method, this algorithm, which this is actually easy now. This approximation on the right-hand side is actually quite easy to program and have a computer solve for us. Right? This is called the left-hand rule because we have indexed the positions and the corresponding heights of these rectangles by using the left-hand edge of each of the rectangle. Right? There's another way we can create a Riemann sum and approximate the area under the curve, again with rectangles, and that's what the next slide is going to show. So here I have the exact same curve, and I've also got the same number of rectangles indicated between limits a and b. But now you can see that the upper edge, the top of each rectangle, the top midpoint of that top edge or top side of each rectangle, as I go up you can see this, touches the function exactly at the midpoint of that top edge. All right? So it's a little different way to try to estimate or represent the area under the curve by not lining up the left-hand edge but the actual midpoint of the upper side or the upper edge of the rectangles with the function itself. Right, so now delta x is the same for all these. All these rectangles still have the same width, and it's very easily calculated with this. Right, so we're just going to do what we did before in the previous slide. We're going to add up all the areas, the individual areas of each rectangle, and use that to approximate the integral. Right, so using the indexing as we did before, lower limit a, we're going to call that x0. Now, granted, x0 still is the left-hand edge of this first rectangle, but you'll notice the height can be found by taking the function not at x0, but adding half of the distance of the width of the rectangle. In other words, this function evaluated not at x0, but at x0 plus half the width of the rectangle. That's delta x over 2. If I evaluate the function there, that tells me the height. Right? So I have to add this extra half width to x0 and evaluate the function there to get the height of the rectangle. Same with the second one. The left-hand edge of rectangle 2 is x1. But now, in order to get the height, I have to add delta x2 to x1 here, and then evaluate the function there. Same with the third rectangle. And then we go all the way out to the nth rectangle as we did before, and evaluate the function at half the width plus that xn minus 1. Right, so it's a little different. However, delta x is still the common factor in all these. So this expression here, up here now, represents every term on the right-hand side is the area of each successive rectangle starting with the first one. So here is the area of rectangle 1, area of rectangle 2. You can see that common factor delta x. Finally, adding everything up to make it look a little more economic, which also is a Riemann sum. And we're indexing from 0 again to n minus 1, right? This is the new algorithm, or evaluating the function at this position now, gives us what's called the midpoint rule. It's a little bit different approach than the left-hand rule. Right, so those are two algorithms, the left-hand rule from the previous slide and this one, the midpoint rule. This is using rectangles to try to approximate the area of the curve. Now we can improve on this if we change the shape. Right, so look at the next slide here. Once again, this is that exact same function. Right? Now, instead of rectangles, you can see I have dotted lines drawn. Right? Each of these dotted lines is separated by a distance dx, and I've got an integral number of them fitting between a and b here. All right? And so instead of rectangles, I'm going to use a trapezoid now to try to approximate what is happening under that curve. Delta x can be easily calculated again, by the way. Right? In this case, I have n delta x intervals, not n shapes yet. Right? So look at this first thing. See that yellow piece pop up? That is a trapezoid. Now it doesn't. It looks like this function here, this blue line. The function is actually curved. If you look really close, you can see that this is really a trapezoid. There's a straight line connecting this dotted line, this point here, to that point there. I have indicated by the little arrow. All right, but it is actually a straight line, and it doesn't fit perfectly the curve. But if as I add more of these, there's another rectangle. You can see there's a gap now. Especially you'll be able to see it here. See, it doesn't quite fit perfectly, but I think you would all agree that this is doing a bit better job than those rectangles were doing. Right? You can see we're missing some. There's a little gap there. We're undershooting. Right? We're going to overshoot here, you can see. See that? Right? So these are straight lines. So we're using trapezoids now. All right? And so instead of using the area of rectangles, we're going to use the area of trapezoids. And you're going to see that this algorithm does a little better than using rectangles. Right? So it's a different shape, a little better approach when you have such curved functions like this. Right? So how do we go about this? Remember, you may remember this from back in history sometime, that the area of a trapezoid is the base times the average height of the trapezoid. Well, this will be easy to write down the area of each one of these trapezoids that contributes to the area under the curve from limits A to B, right? Because the width, or the base, delta x, is the same for each of them. And so all we have to do is multiply delta x, in each case, by the average height of these things. All right, so let's look at this first rectangle here. Right, there is the expression for the area. I called it A1. That's this rectangle number 1. You can see it's the base times, and you'll notice this second term here is the arithmetic average of the height. All right, there's actually two heights involved. The height of the short side, in this case of the rectangle, is evaluated at f of x0. The taller side is f of x1. Add those two and divide by 2. That's the average height of that trapezoid. I may have called that a rectangle a moment ago. These, of course, are trapezoids. Right? So, and then trapezoid 2, trapezoid 3, 4, and so on will have a similar term. And so if you add them all up, we can approximate the integral from A to B with this expression. You'll recognize this as the area of the first trapezoid. Here is the area of the second trapezoid, and you go on and on until you get to the last trapezoid, which is this one. And you can look at that more closely and stop the video if you need to and think it through. It might be good for you to actually write this out by hand, convince yourself. I can make this a little more economic notation if I do this, where I have factored out the common delta x term. And you'll notice what happens here, and this should be obvious, that by taking the average height of each successive rectangle, you'll notice that f of x0 and f of xn, the function is only evaluated at the endpoints, which happen to coincide with the limits a and b. Those only show up one time here. The function is evaluated twice in the numerator here for every internal point from x1 out to xn minus 1 here. So you can see the summation shows up there. Of course, there's a common factor of 2 here for these. All right, so I think it will be good. It's very, very easy to do if you write this out by hand, do a little bit of algebra. But you can convince yourself that this indeed is the right economic expression for this larger expression where we've added up directly all the areas of the trapezoids. Right? This, of course, then is called the trapezoid rule. And you will find in the next guided activity that this is actually more accurate for a given number of shapes than the Riemann sum approach. Right? All right, well, there's one more algorithm I'm going to point to, and I'm not going to provide a geometric version of it. I'm just going to more or less show you the equation in this form. But you can imagine, instead of using straight lines connecting these points, like we did with the trapezoids, you could imagine using an actual curve. A curve would be better, even though you might not have the exact curve between here, but you can imagine using a parabola. Now, mathematically, to do this properly, you would have to include 3 points. So, for instance, this point, and this point, we could include a parabolic approximation here. And so this leads to something called the Simpsons rules, right? And I'm not gonna, like I said, I don't have a slide which shows you geometrically. You really can't quite represent this geometrically. But if you want to look a little more in depth, you can look at that the relevant chapter in that numerical methods book. I'm going to fast forward about 2 slides. You can see how this slide works. I'm not going to emphasize it because it really is the same. It's just a different way of doing rectangles, but it has the same order of magnitude of error as the trapezoid rule. So don't worry about this one. I'm just going to fly through this. This is the Simpsons. It's called the Simpson 1/3 rule. All right, and it's equivalent to taking the area under a parabola connecting 3 points. All right, and it may or may not be obvious why in the world these 2 summations occur, but this is what happens for odd number indexes. You have a factor 4 multiplying the function, the summation of the function. For even number indexes, you have a factor of 2. This is just how it works out mathematically. And also I want to point out f of x0 and f of xn in the numerator here also are just used one time. They're just evaluated one time, very much like the trapezoid rule. Right? And there is a little different factor here, 3. This is why it's called the Simpson 1/3 rule. Well, once you've generated these types of expressions, you can use this, and it's actually quite easy to program. Might not be particularly obvious where this comes from. That's why I'm going to point you back and look at the book. Right? So that the Riemann sum rule, the trapezoid rule, and this Simpson's 1/3 rule are what we're going to be programming now in the next guided activity. All right, so that's it for now. Please be careful, drive home safely, and may the force be with you.